So this topic is talking about limits at infinity. So before we kind of had a little bit of a conversation about end behavior, right? And that's going to come up again now. I think I used the words end behavior when talking about limits to the left or right, but now we're going to really like formalize that idea into this conversation about limits as x goes to infinity or limit as x goes to negative infinity. So just as we can take this limit as x approaches some finite value, what have I just said? Well, what happens if x increases forever and ever and ever without any bound? Well, there ends up being a lot of ideas that pop out that we're like pretty familiar with once we start talking about these limits at infinity, and they relate to that idea of an asymptote. So if we remember before, right, the limit as x goes to like a, maybe from the right of a function, gave us some infinite value, then that means to the right of that point a, our function is doing something like this, maybe, and then it's just doing whatever everywhere else. And maybe we would say to the left of a, sorry, I'm trying to erase. Maybe to the left of a, our function is going to go to negative infinity. So now over here, maybe we have something like this, right? And this corresponds to what we like to call a vertical asymptote. And those were our limits at finite values. Well, now, what would it look like if a limit as x goes to infinity of our function was to exist, right? So this would mean that, if I start off maybe with just intercepting the y-axis right there, but I said this limit as x goes to infinity of my function is equal to something like -1, well then what can that look like? Well, that means as my function is plugging in larger and larger and larger values, I have to be getting close to specifically one value, -1, right? To be a limit, I have to be approaching that value forever and ever and ever. I can't start just going away from that. I can't bend and go crazy. I have to approach this output value of -1. So the way that I've set this up so far, maybe it looks like this. And again, this line is going to go on forever and ever and ever, approaching -1. So in that sense, it's kind of like this vertical asymptote, but instead of this line going forever and ever and ever upwards, I'm going forever and ever and ever closer to the output value of -1. So in that sense, instead of a vertical asymptote, we have a horizontal asymptote. And we can formalize this a bit with this theorem. If the limit as x goes to positive or negative infinity, right? I'm okay with this happening to the left as well, right? Because if I did the same thing but like over here, and I also got an asymptote, then I also want to include that here. So if the limit from negative or positive infinity of my function is equal to L, right? So it exists and it is some number, then f of x has a horizontal asymptote, and we like to describe these as equations of lines, right? For a vertical asymptote, we had something like x is equal to something like 2, or in this case, right, I said this happens at a, so really we want x is equal to a. So for a vertical asymptote, we have x is equal to a. But what is the equation of a horizontal line? Well, that's just y is equal to whatever that value is. In our case, y is equal to L. So again, we may have two horizontal asymptotes. Maybe from positive infinity and negative infinity we reach a different limit, right? But they might both exist. Well, they may also just not even exist at all. So let's take, for instance, the limit as x goes to infinity of the function x squared. Well, if I plug in larger and larger and larger numbers, right? If I plug in 10, then I get 10 squared is 100. If I plug in 1,000, right, then I get 1,000 squared is, we're going to have 6 zeros, so a million, right? And if I plug in something with just a whole lot of zeros, and I square that, I'm going to end up with something with a whole lot of even more zeros, right? So this limit, as my x value increases, my output, x squared, must also increase without bound as well. So this limit is also just infinity, right? If I plug something huge into the function x squared, I get something huge without ever limiting that value. So as x increases without bound, sorry, as our inputs increase without bound, so do our outputs. Well then, what about the limit as x goes to negative infinity of x squared? Well, if I plug in a huge negative number, so like negative 10, negative 1,000, negative whatever this huge number is, well then I square that, I'm going to end up with a large positive number, right? A negative times a negative becomes a positive. So my left in behavior, my limit as x goes to negative infinity of x squared is also going to be positive infinity. Now again, does this mean I have an asymptote? No, right? Infinity is not some number L, right? Saying y equals infinity does not make any sense at all, right? I can't possibly graph that line. We only have horizontal asymptotes when those limits approach actual genuine numbers, right? And infinity is not a number. It is a concept describing the fact that this limit increases without bound. And we even say, technically, if a limit goes to infinity, that still doesn't exist. Well, now let's take, for instance, the limit as x goes to infinity of 1 over x. So if I plug in something like 10, well then 1/10 we can also write as just 0.1. If I plug in something like 1,000, well I can write that as a decimal 0.001, right, 1,000th. Well then if I plug in something even just way more huge, dot 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 dot, well this is going to be however many zeros it takes to write this as something very, very, very small. So if I plug in larger and larger and larger values for x, I'm getting smaller and smaller and smaller outputs. And I don't mean more negative, I mean smaller in size, right? 0.1, 0.001, 0.000000000000000000001, however many zeros it takes, right? So these infinitely small things, what value are all of these approaching? Well, they're heading towards zero. So this is a horizontal asymptote. For a horizontal asymptote, that's y equals 0. Why? Well, hey, let's look at the graph of this function. It's going to look like this. I guess I didn't really need to mark the coordinates, especially not when it messed up like that. Um, so as I plug in infinity, I'm getting infinitely small, and I go to 0. So because this left-hand limit, or sorry, this right-hand limit, not hand, end, the right end behavior limit exists and is equal to 0, then I say I have a horizontal asymptote y equals 0. Really, yeah, we have a horizontal asymptote y equals 0. Very good. But again, this is happening the way that I'm drawing it right now, as if things happen simultaneously graphically and algebraically. In truth, at this point, our hope is that you are going to be able to figure out these limits at infinity, even just through a purely algebraic standpoint. And there's an idea that I talked about like towards the start of class, right? If I have the limit as x goes to infinity, and I have something like x cubed minus x squared plus 20 or 200x minus 1, it turns out only one of these terms are actually going to matter, right? When I take this limit, if I plug in something like 1, well then if x is just equal to 1, right, then 1 cubed minus 1 squared plus 200 times 1 minus 1, well hey, 1 minus 1 plus 200 minus 1, well that's 199. So at values like x equals 1, what feels like the most dominating term? Well, it feels like this 200x is going to be really powerful, right? But I plugged in a really small number that made it get really outweighed by the fact that we're multiplying by 200 on that coefficient. If I plugged in something that was really big, like 100, or sorry, even just something kind of big, like 100, then when I plug that into this function, right, I get 100 cubed minus 100 squared plus 200 times 100 minus 1. Well, 100 squared is 10,000, and 100 cubed is a million, right? Plus 200 times 100, we'll just add the number of zeros, right? So 20,000, and then minus 1. Well, hey, 100,000 minus, wait, did I do that right? How many zeros? Yeah, okay. Uh, there we are. Okay. 100,000 plus 20,000, sorry, negative 100,000. I keep saying it wrong. Look, just look at the algebra here, right? Negative 10,000 plus 20,000 gives me positive 10,000, and then minus 1, and then this 1 million right here. Well, even just by plugging in 10, or sorry, by plugging in 100, suddenly the terms don't really look like they're talking, right? They're in the same magnitude, right? My x cubed term gave me a million, while my x squared only gave me 10,000, and even my 200 times 100 term gave me 20,000. Well, now if I only plugged in something like 1,000, well then my cube term is going to give me, right, three sets of three zeros. My squared is only going to give me six sets of zeros. And then I have plus 200 times 1,000, which is going to be, and then a minus 1. Well, 200 times 1,000 is just going to be 200,000, right? So now my cube term is at a billion, my squared term is at a million, and my 200 times x is still only in the hundreds of thousands. So, like, this is not, right, in the world of numbers, a very big number, right? 1,000 is nowhere near as big of a number as we can even just think of, much less write down. But we're already seeing that there's a lot of weight in this higher term, right? By cubing, I've done a whole lot more, right? I've reached such a higher value than I did by squaring or even multiplying by a coefficient of 200. And certainly this minus 1 is doing like nothing in the end, right? So the idea that I'm trying to get across is that when it comes to polynomials, all we end up caring about is whatever the highest exponent is, right? The leading term is going to completely determine the end result of the function. And even so, right, this is minus x squared. Maybe we're afraid that subtracting x squared is going to affect the end result. But it turns out if I plug in something with even just 3 zeros, my x squared term is still at a million, while my x cubed term is at a billion, right? So once I do this difference, I am still at 999 million, or nope, uh, yeah, no. Sorry, all these zeros and suddenly I can't do that math. Yeah, 900 million and then plus 200,000 minus 1. Which still is like huge, right? Compare 900 million to just 1 million, and these are vastly different numbers. That is 900 times as large. And all we did was plug in something with 3 zeros. If I would have plugged in something with 4 zeros, this would have been even more of a massive difference between x cubed and x squared. So again, the leading power here is going to completely outweigh anything else happening in the polynomial. So in that sense, whenever we have a limit at positive or negative infinity of a polynomial, we only care about the leading term. So the idea here, right, is that this is going to equal infinity, and only because my x cubed tells me so. If now I would have done the limit as x goes to negative infinity of x cubed plus, or this was minus 2x, sorry, minus x squared plus 200x minus 1. Now I'm plugging in something huge and negative. And again, I'm going to actually just not even care what the other terms do. Because whenever I'm adding things together, if something just has way more zeros than the rest of the terms, they're not even going to do anything to it, right? They're going to put hardly even a dent into that. So this is just going to be equal to the limit as x goes to negative infinity of x cubed. Well, when I plug something negative into a cube, that's a negative times a negative times a negative. Well, the first negative times a negative turns into a positive. Positive times that third negative turns back into a negative. That is going to be a negative number, and these negatives are just going to get right more and more and more negative, and so this is going to go to negative infinity. So again, this limit of this polynomial is just completely determined by the leading term. In fact, if instead I had the limit as x goes to negative infinity of negative x to the fifth plus 40,000 x squared minus 1, then yeah, I still don't even care about 40,000 x squared, because if I plug in 40,000 into this function, right, this would be 40k to the fifth, right, negative 40k to the fifth, plus 40k times 40k squared is just going to be 40k to the third. And which one of these is bigger, 40k to the fifth or 40k to the third? 40k to the fifth, by a long shot, is going to be way larger than 40k cubed. So no matter what the coefficients are, we really don't care. The leading term is going to completely determine the end behavior. So this limit, we can just drop everything else. Limit as x goes to negative infinity of x to the negative fifth. I think I deleted some of that there. Well, now this is an odd power, so when we multiply it or put a negative into here, that result is going to be a negative. But then we're also multiplying that by this negative sign out front. So x to the fifth would give us negative infinity, but the negative sign there is going to switch this to a positive infinity. But again, that's just completely determined by the leading term. And it's not that, again, this is, I'm trying to emphasize here, we don't just want the power, we also want the coefficient, right? Because if this is negative or positive, that will change the sign potentially of the end behavior, right, of that infinity, whether it's positive or negative infinity. Now, the thing happening here now is, let's say, that I have the function 1 over x squared plus 1. What is this end behavior going to do? Well, kind of the same way that we had 1 over x, right? The limit as x goes to infinity of something, right? This is going to look like, right? So this isn't actually good algebra right now, but I'm going to write it out just to help us understand that x squared plus 1 is going to go to infinity. Well, 1 over infinity, when we're thinking in the world of limits, dividing by something infinitely large gives me something infinitely small, aka this goes to 0. So this is kind of how we should be thinking about these things, but algebraically, it is nonsense to plug in infinity, and even more so to try and divide by infinity to get 0. In the world of limits, this is perfectly good and valid and makes sense. However, in the world of algebra, right, we can't earnestly be doing these things, right? Um, but yeah, this is how they really evaluate. So you should be thinking of this kind of process in your head, um, but be careful, this isn't technically the totally precise algebra to do this stuff, right? So let's say, for instance, too, limit as x goes to infinity of x squared over x squared plus 1. Well, like I kind of said before, the limit of these pieces is going to be entirely determined by the leading coefficient of all of our polynomials. So on the bottom, it is just going to look like x squared, and on top, it's just going to look like x squared, because that's really all that we have, right? So this is going to look like this limit. But x squared divided by x squared, hey, that's just a number divided by itself is going to be 1, as long as that number is not 0, right? But if we're going to infinity, we're certainly not 0. So this is just going to look like the limit as x goes to infinity of 1, which is just 1. So in that sense, we see a horizontal asymptote for this function, and that is going to be, right, y equals 1. But again, that's for this function right there. Now, there's another way to do this that is a lot more algebraically precise, and the homework is going to walk you through something like this, right? So what if we had this limit, and then I want to multiply top and bottom by 1 over x squared. Well, then x squared on top turns into x squared over x squared, and then this on bottom turns into x squared plus 1 over x squared, right? And this is this limit still. Well, x squared over x squared turns into 1. Limit as x goes to infinity. X squared over x squared turns into 1. x squared plus 1 divided by x squared will then distribute that fraction or that division to both parts, turns into x squared over x squared plus 1 over x squared. So this is now the limit as x goes to infinity of 1 over 1 plus 1 over x squared. Well, now does this bottom limit actually exist? Yeah, right? Our rule for doing all of our limit rules is if we're looking at a fraction, I can just take the limit to top and bottom if the top and bottom exist. Well, the way that I wrote it before, this would look like infinity, right? If I look at it just like this would go to infinity over infinity, which neither of those are supposed to exist, right? So, looking at it here, once I've redone this algebra, this is the limit as x goes to infinity of 1, right? Does that exist? Yeah. Over the limit as x goes to infinity of 1 plus 1 over x squared. Does that limit exist? Well, sure. This is just 1 over, right? 1 plus, and then we want to distribute the limit to both parts. And then we already know the limit as x goes to infinity of 1 is 1. Limit as x goes to infinity of 1 over x squared. Well, hey, that's just 0. So this is 1 over 1 plus 0, which is just 1 over 1. Well, hey, that's still just 1, right? We go back to being as simple as 1. So we can do this kind of informally here to understand how this really works, but the algebra kind of necessary to do things in a very valid sense sometimes requires a little bit of clever work, which ultimately that clever work just turns into divide by that leading power, right? Whatever the highest power of x is, if you just divide through by that, then that should work out the way that you want it to. Well, now, I've done so much where I keep getting results, right? I took a limit as x goes to infinity, I get positive or negative infinity. Sometimes I get actual numbers, just like that previous example, but that is not always going to be the case. And in fact, there is a very normal function that we see in calculus, a lot of them, who does who we can ask this end behavior for. Well, if we look at this graph, this sine is going to be this wave function forever and ever and ever. And as x goes to infinity, is there ever actually any number that I approach? No. Do I increase without bound? No. So I certainly can't be infinity or negative infinity. I'm stuck between 1 and negative 1, but am I ever approaching any of those numbers? No. So we actually would say this limit as x goes to infinity of sine does not exist. It doesn't exist just straight out. It's not that it even doesn't exist because it goes to infinity. I can't even say it goes to infinity. So this is like the least sensible limit of all. This is just doing nothing, right? So if I even had, right, limit as x goes to infinity of 1 over sine, right, this also isn't going to exist because I'm just going to be dividing by things that keep bouncing back and forth between negative 1 and 1. But is this a graph that I can make sense of? Well, not really, right? Like, I don't have a picture of dividing by this in my head. Oh, wait. Yeah, we do. Cosecant. And does that graph make sense? Well, I certainly don't feel like drawing that graph right now. But does it make sense that this does not go to any number or even go to infinity? Right. This is periodic. It's going to repeat forever and ever and ever. Yeah, this is not going to do anything sensible. Now, the last piece that I want to introduce is something called L'Hopital's rule. And that says if the limit of a fraction, right, f over g of two functions is or would give 0 over 0 or infinity over infinity, then the limit as x goes to a, we can just take the derivative of the top and the derivative of the bottom, and that's going to be equal to the original limit. So let me maybe be a bit more careful with how I'm doing this. Then the limit of f of x over g of x is equal to the limit of f prime over g prime. So again, this is not the quotient rule, right? Our quotient rule requires a whole lot more work, right? F prime times g minus g prime times f all over g squared. That is nothing close to what's happening here. I just take the derivative of the top and the derivative of the bottom and just keep writing it like that. So maybe look at this example, x squared plus 1, limit as x goes to infinity, of x squared plus 1 over x, right? Right now, if I tried to plug this in, this would look like infinity over infinity. So L'Hopital's rule says I can take the derivative, or this is going to be equal to, when I take the derivative of both pieces, derivative of x is 1, derivative of 2x plus 1 is 2x. Well, hey, I can see pretty clearly now the limit as x goes to infinity of 2x over 1. Well, hey, that's just 2x, and this is going to go off to infinity. Right, so L'Hopital's rule can make things like painfully simple sometimes. However, this is kind of a tool that I don't recommend using unless we just like have to, unless we very much get stuck, right? The thing that I would prefer us to do is say this is the limit as x goes to infinity of, well, I can divide both parts by the x. So I have x squared over x plus 1 over x. Well, this is the limit as x goes to infinity. X squared over x is just x. 1 over x. I don't get to write any more simple. Well, as x goes to infinity, x goes to infinity, and 1 over x goes to 0. So infinity plus 0, well, hey, that's just infinity, right? So we could have taken that limit. We didn't get stuck necessarily. But L'Hopital's rule is kind of like, um, what's the expression? Like driving a hammer in with a semi-truck, right? We're using something way too strong than is necessary, but it certainly gets the job done, right? Now, and this is what I'm kind of confused by because it's not super clear to me when we're supposed to use L'Hopital's rule in this class because I didn't see it like in the regular course stuff. However, it is a very necessary thing to teach in calculus, I believe, so I felt it necessary to introduce it here. But I also do want to kind of warn against L'Hopital's rule even more so because sometimes we might be tempted to use it when we really almost shouldn't be. Sometimes L'Hopital's rule is going to give us more work than we really need. So let's consider this rational function. Limit as x goes to infinity of 2x to the fifth plus 3x squared minus 11 over 5x to the fifth minus x to the fourth plus 7x. Okay, well, if I took L'Hopital's rule, this would keep being infinity for like 5 derivatives. So I'd have to take a few derivatives. And that's not, the worst thing in the world to do, but what I'm going to do is even simpler, right? Because it turns out, well, hey, I only care about the leading coefficient in a polynomial. So this limit as x goes to infinity, right? Because we're so clever, I say, okay, I only care about the leading term. So this is just going to be 2x to the fifth and the bottom part is only going to be 5x to the fifth. Those are the only terms that I actually care about, so this will evaluate to the same thing. Well, now 2x to the fifth over 5x to the fifth, well, hey, my fifths cancel, or my x to the fifth cancels. So I'm left with just 2 over 5. The limit as x goes to infinity of 2 over 5 is just 2 over 5. And this is true. Yeah, this is the correct limit. However, if I try to take L'Hopital's rule, right, derivative of this part is 10x to the fourth, 6x, and then 25x to the fourth minus 4x cubed plus 7. Okay, well that's still infinity over infinity. Let me take another derivative. 40x cubed plus 6. 25 times 4 is actually 100, so 100x cubed minus 12x squared. Now another derivative, right? 140x squared. Derivative of 6 is 0. Now derivative there, 300x squared minus 24x. Another derivative, 240x over 600x minus 24. Another derivative, 240 over 600. Hey, it turns out that simplifies to like 2/5, right? Wait, did I do something wrong? 10, does that simplify to 2? That looks weird. That doesn't look like it should. Um, oh no, yeah, that absolutely does. Sorry, I confused myself. Um, yeah, that does simplify to 2/5, because 120 fits into both of those terms. 120 or 600 divided by 120 is 5. 240 divided by 120 is 2. So yeah, that is 2/5. But do we want to do all of this? No, because we can just do this simple work here, right? We didn't need L'Hopital's rule. That would have just been overkill. We just recognize the only term that I care about in a polynomial with a limit at infinity is the leading term, right? And this kind of exemplifies I care about the leading term, not just whatever that highest power is, right? Because this did not give me x to the fifth over x to the fifth. That would have been 1. This gave me 2x to the fifth over 5x to the fifth. We care about that entire leading term. Okay, so very good. Um, Now this example kind of does correspond, I would say, to like a little bit more happening. So, uh, um, if we say the limit as x goes to infinity of polynomial over some other polynomial, we're going to do the same process of only caring about the leading terms, but the way that that simplifies out from there is going to differ a lot depending on what the polynomials are. So if I set the limit as x goes to infinity of x squared plus 1 over x cubed minus 11, right, then I know I'm only going to care about the leading terms. This is going to be x squared over x cubed. Well, that's going to be 1 over x, right? So if the denominator has a larger power, that's going to dominate what happens with the function, right? We're going to go to 0. However, if the top has a higher power, something like x cubed minus 11 over x squared plus 1, well then, again, delete all the other terms that aren't the leading term, x cubed over x squared. So the limit as x goes to infinity of x, well now, that goes to positive infinity. But again, limit as x goes to negative infinity of the same thing would have been the limit as x goes to negative infinity of x, which is now negative infinity. So, in that sense, right, we care a lot about what term this simplifies to, right? We had an x squared on bottom and an x cubed on top, and the signs do end up like mattering a lot. I'm sorry, I forgot to write a negative infinity right there on that limit. Yeah. So maybe I'm overemphasizing something that doesn't need to be overemphasized, but when we do the simplification, right, this could give us terms that are odd, which means we really do care about whether we're taking negative or positive infinity limits. Okay. But that same battle is going to happen throughout all of these. With any rational function, it ends up just being a battle between the top and the bottom, but only those leading terms. Okay, very good. So that's this section. That's all I want to say about this section, I guess.